Alright, here's the solution to problem number 10 for the practice problems for Newton's laws. Here we have a bodybuilder holding two ends of a rope with a mass attached in the middle. We're given the angle theta, which appears in the diagram, which is the angle is 4.5 degrees, and we're also given the mass of the ball, which is 15 kilograms. So the first thing I'm going to do is draw the free body diagram for the ball. Okay, the first thing is we know that one of the forces is the weight of the ball, which is downwards. We also know that there are two other forces. There's the tension of the rope, which is up and to the right, and there's the tension in the rope, which is up and to the left. Okay. Now, there's one thing we should note, and that is that the angle theta, which appears in the figure, actually appears is the same as the angle right here. That angle right there. So, and that angle is obviously 4.5 degrees. So, the thing to note as well is that this mass is in static equilibrium, which means that the net force is equal to 0. So the sum of all of our forces should be 0. And you know what, I haven't labeled any of our forces, so I'm going to call the weight W. This force here I'll call T1, and this force over here, which is T2. One thing to note about T1 and T2 is that they have the same magnitude because they're the same rope. Remember, the tension on the rope should be the same everywhere. So we have T1 should equal T2. Remember, these are magnitudes. So let's go ahead and write down the equations of motion. In the x direction, we have the following. Well, we have the x component of T2 and the x component of T1. And since this is in static equilibrium, these components should equal 0. Note that there's no x component for the weight. And in the y direction, we have the y component of T2, the y component of T1, and the y component of the weight. And again, since this is in static equilibrium, the sum of these components should equal 0. Alright, now, where do we go from here? Well, let's look at the first equation in the x direction. There's no surprise here that the x component of T2 should be the same, except the negative of T1x. What else can we say? Well, we know because of the symmetry that T2y and T1y are going to be the same. So I can replace them with a single term, which is 2 times 1y. And this is going to equal minus the y component of the weight. Here I'm going to keep the acceleration due to gravity as negative 9.8 meters per second squared. Okay, so that's the acceleration due to gravity. What's left to do is we can actually now solve for the y component of our tension, which is just negative times the mass times the acceleration due to gravity divided by 2. And, well, plugging the numbers in your calculator and all of that, we should get 73.5 newtons. You can double check that for me. Okay, so we have the y component. How do we get the x component? Well, if we go back to our free body diagram, note we have this triangle right here. T1y and T1x are the sides of that right angle triangle I just drew. So if I look at the tan of my angle theta, that should equal the ratio of T1y over T2x. sorry, not T2, T1x. So I can solve for T1x, and that's just T1y over tan of theta, which is 4.5 degrees. So I know what T1y is. It's the 73. I can plug that into this ratio, and what I'll find is that the x component of T1 is 933, I believe, newtons. So I can write down the tension as a vector with components 930, well, this is T1, 933 and 73.5 newtons. Okay. If I want the magnitude, I could use Pythagoras' theorem. I compute the square root of 933 squared plus 73.5 squared, and you should get something close to 936 newtons. And again, the problem is to two significant figures, so I'm going to round this to 940 newtons. All right, that's it.